So basically, we say that f has an isolated singularity. At A, which is a point in the domain, if simply f is holomorphic everywhere in G, but possibly at this point. So informally, so we want to, in a way, we want to classify how bad the singularity is. And informally, let me just, even before the discussion, let me state the classification is, so just ignorable, so f is in fact holomorphic everywhere, not only in second case, it's series of cases, it's if f is as bad as 1 over z minus a to the n, and the last case is f is as bad as, let's say, x 1 over z at 0. So, in a way, I mean, first kind, it means just that we added this point to singularities by some mistake, and we want to learn how to deal with this, how to really deal with singularities which exist. Second, well, that's in a way algebraic by nature. And third, it's clear that it looks different from one of these. But we'll learn very explicitly how to classify this. So, yeah. So the first kind has a name. So an isolated singularity A is removable for f. If f extends holomorphically. Yeah. So of course this is a local question. It's a question about punctured disk and disk around this point. And here is the theorem. F is, suppose that F is bounded in some punctured disk around A inside G, then F is holomorphic in the whole G. So yeah, and the proof is easy. So take so define a function h of z is z minus a squared f of z when z is not equal to a, and let's say 0 if z equals to a. We'll see that this function is continuous and actually holomorphic. So let's see. Let's take this expression which leads to derivative. So consider h of z minus h of a divided by z minus a. So we see that this expression so this so we can consider it when z is in the function. So let's see. The first factor is bounded, and the second factor has a limit equal to 0 when z tends to a. So limit a z minus a is 0. Limit yes, and f of z is less than capital M. So it's bounded. So it follows that limit h of z minus h of a z minus a z tends to 0 to a, sorry, exists and equals to 0. So we get that h thus h defined as we did is not only continuous in G but holomorphic everywhere, including 0. And also h of a is 0 and h prime of a is also 0. Now recall, so we have a theorem, so by the theorem about zeros of functions. H of z is, so we know that since first two coefficients vanish, Taylor expansion of h starts at least from second term, I mean from term with z minus a squared. So h of z is z minus a squared, g of z, everywhere in G, and G is holomorphic. Well, but also in G without A, h of z is z minus a squared f of z. But this means that f equals to g in g minus a. But G is holomorphic in the whole capital G, then F extends to A, and the singularity is removed. Okay, so this, this is the standard way of treatment of singularity. So we see that if something happens at this point, then the function is unbounded in any neighborhood of the point. So actually, this leads to another level of classification. So, definition. Suppose that F is holomorphic in G minus A is isolated, not removable. Then there's further classification. Namely, if for some n the limit exists and is not zero, then F has a pole of order n or degree n at A. And so last definition for this classification, I promised three types. Something which we ignore, something like 1 over z minus a to some order, and this is exactly of this type, right? So if we take 1 over z minus a to some degree and then multiply by the same expression, then we'll get a constant. So it will have a limit. And the last definition is not removable, not essential, not pole of any order for F which is called G minus A, and then Z equals to A is essential. So I'm not checking this now, but trust me that here we have an essential singularity at 0. Now there's a statement we don't prove. There's a big fact. That a function around essential singularity behaves as randomly as possible. So, so it's called Picard-Gray theorem. So if you try to visualize what it means, you'll see how bad things are. So suppose that F is holomorphic on the complement to A, and A is essential. Then, for every punctured disk, K prime A R around this point inside G. The image of this punched disk inside C is either the whole C or C minus 1 point. So no matter how small neighborhood you take, throw away the point where your function is not defined, the image will still be like this. So you come closer and closer to the point, but still in this small neighborhood, its image will be everywhere. So, I mean, you cannot hope that by coming very close, you will not get, you will not touch, say, the points 100 and 200 together, right? So you fix 2 points in complex plane. The theorem guarantees that no matter how close you come to the singularity, the image of the punched disk around will contain one of the 2 points. Okay? So I don't think I can draw anything about it, but if you try to put this fact into your head, you'll see that behavior around essential singularity is very, very random. Good. So we do not prove this. So, remark. We do not prove this. But we prove the following theorem. So we have an essential singularity. So then, for every radius, f of punched disk of this radius is dense in C. So, of course, it's a much weaker statement than this fact. This fact actually describes the image. So certainly C itself, or C without 1 point, is dense in C. But at least the statement means that no matter what happens, in a very, very small neighborhood, there will be points whose images comes very close to every given point. So let's prove it. Suppose not true. Yeah, so suppose there is a complex number C such that for some R, the intersection of a disk of radius epsilon around this point and the image of some punched disk is empty. So, yeah, so then absolute value of f of z minus c is always greater than epsilon. Z this punched disk. Well, of course, if something is guaranteed not to be 0, you invert it. So let's take g of z, which is 1 over f of z minus c. So what we wrote means that it's bounded. This function is bounded in everything. Then the singularity is removable for G. But since it's removable, then G of A is defined. Well, then there are cases if G of A is not 0, then we can define f equal to 1 over G of Z plus C, and it will be defined at 0 at A. So f will have a removable singularity, or if G of A is 0, then of course we cannot divide in holomorphic functions. But then G of Z is Z minus A to some power times H of Z, where H of A is not. Then we can still define f of z, which will be c plus 1 over z minus a to the n, 1 over h of z, and then we'll see that this formula works for z not equal to a, but we'll see that z minus a to the n f of z has exists. So then z equal a becomes a pole. But by our assumptions, it was neither. Neither was true. So we got a second. Good. Okay, so our last topic for today is typical examples of poles, namely rational functions. So, just by the definition, a rational function is a ratio of two polynomials. Definition. A rational function. And on C is f of z, which is, let's say, p of z over q of z. P, Q are polynomials over there. So, remark is that by the main theorem of algebra, Q of z can be presented uniquely as some constant, which doesn't matter, times a product of powers of linear polynomials. And let's say that we removed common divisors from this expression. Such expression, of course, is not unique. We can multiply both the numerator and the denominator by something. It will be the same function, but let's say that greatest common divisor of P of z and Q of z equals to 1. So then f of z, as we see, is P of z divided by C minus A1 P1 z minus A K. Yeah, and I put these factors into groups in such a way that AI would be different from AJ, I different from J. Otherwise, I would put several factors into one with a bigger exponent. So, looking at this expression, we see that f is holomorphic outside these points. Obviously, because when you throw away these points, the denominator becomes invertible. And also, f of z has a pole of order mi at ai. So to see that, we need to multiply. So we get rid of one of the factors. So if we take z minus ai mi f of z, then this function has no singularity. In a disk around R, where R is chosen in such a way that R is smaller than the distance between AI and any other AJ. So if we throw away all others and then multiply by this factor will be erased from the denominator, and then this function becomes holomorphic there. So defined in particular at AI, the limit will exist. So it has a pole of order mi at this point. Okay, so in this sense, rational function is a typical function with poles. So before I continue, let me make a remark about the previous. So on poles. So suppose that f of z has a pole of say m at A. So this means that it's holomorphic on some complement of A, and g of z, which is z minus A to the m f of z, is holomorphic, say, in some disk around A. And g of A is not zero. So then we can take its expansion, take the Taylor expansion of g of z at A. So it will start from so g of z becomes, let's say, C0 plus C1 z minus A plus C2 z minus A squared. I'm not even interested in these coefficients right now. Dot, dot, dot. And then the last one will be Cm z minus A to the m plus everything else, but I won't be interested in the rest of them. Actually, even m minus 1, as m minus 1. It's the last one I'm interested in. Of course, there's the whole tail of these. What I want to say is that these coefficients are canonically defined. They are derivatives or related to derivatives of g of z. Now, define polar part of f z to be this expression, C0 divided by z minus A to the m, plus so on, plus Cm minus 1 divided by z minus A. Well, what I want to emphasize before we pass to standard expression for rational functions is actually I should emphasize the point. F, A, Z. It's polar part. So this function p of f a z, so what do we know about it? It's holomorphic outside A. It is defined canonically by f and A, because we started from f and we obtained this expression by basically, so G was defined canonically, and the Taylor expansion was also defined canonically, so the polar part is given by f and the point. We didn't make any choices. Now consider the function f of z minus p, so this is the last property, p f a z, has no pole, so has a removable singularity. At A. So let me leave this as an exercise. It's a very easy calculation. It just, I mean, you see that you take this difference and there, the polar part just vanishes. Okay, so it's a very important observation, even though I didn't give it a big name, but that's what we will need. So now the theorem, which I will do my best to prove in the remaining time. So let f of z be a rational function. Then there exists unique presentation. And q of z is some constant times z minus a1 m1, z minus a k m k, as before. Presentation of f in the following way. So f is f naught, which is a polynomial, and then sum over the singular points. J for 1 to k, sum over order of poles, some coefficient, by, so L goes from 1 to m really. So it's a polynomial, and then sum of polar parts. Okay. So this is like a presentation of f as a sum of simple rational function. So I will not talk about, I don't have time to talk about uniqueness. Let me prove existence, because it's interesting. So let me make a remark that even though we are studying complex analysis, this fact is algebraic. So only our proof will be analytic, so it works over some other field which is not complex numbers. So we will not use, so an actual proof doesn't use complex numbers. That's correct. How our proof will be proof of existence of the differential. So first of all, divide. So first step, divide with residue. So f of z, which was p of z over q of z, will be f naught of z plus r of z over q of z, where degree of r is strictly less than degree of q. I mean, this is algebraic procedure. We divide this polynomial by this polynomial with residue. Now the remaining thing, so take this function r over q. Well, certainly it's holomorphic in the complement of a1 ar. Subtract polar parts. So I think I have just enough time to do it. So consider R over Q of Z. And let's subtract polar part for R over Q at A1 Z, subtract polar part of R over Q over A2 Z, and so on. So after each subtraction, the function will stay holomorphic at the complement of the next points, of the previous points, but one more point will make a removable singularity. So after this procedure, after subtraction, all A1, AM become removable, basically by claim which I put over there. So we get a new function, call it, I don't know, h of z. So h of z is holomorphic on the whole of the plane, but also it is bounded. Moreover, limit of h of z for z going to infinity equals to 0 for the following reason. So indeed, so for each of the polar parts, and this is true, so for each 1 over z minus ai to mi, this is true. And also notice that the starting function, so degree r is strictly less than degree of q, it follows that the limit for z tending to infinity r of z over q of z is also 0, because denominator grows much faster than numerator. So then the total limit is 0, as I said. So it follows that h of z is holomorphic everywhere and bounded. Now this is possible only in one case, when it's constant. H of z is constant, but then its limit at infinity equals this constant. So then h is completely 0. So what we proved is that we realized that r of z over q of z is sum of these polar parts, which means that f is f naught plus sum of polar parts, and each of them was of the form sum c k over z minus aj to the power k, if you remember, or maybe mj minus something like this. So it's exactly the form we want. So this is the proof of existence, as I announced. I will prove uniqueness on Thursday, but mostly we'll talk about meromorphic functions and Lorentz series. Questions? as I promised, so my promise was negative. You will not hear anything about the results before Thursday, but the positive part is that I'm doing all I can so that you will get